Mass-energy equivalence. When we light a Bunsen burner, energy is released. But where does this energy come from? In radioactive decay, a stationary particle suddenly releases a high-speed particle. Where does this energy come from? Einstein solved the problem by realizing that mass is simply another form of energy, and in these two cases, and all others, there is a loss of mass, leading to a release of energy. He gave us the famous equation E equals mc squared, where E is the energy in joules, m the mass in kilograms, and c the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second. C being so big means that tiny mass changes can lead to large amounts of energy being released. In chemical reactions, this mass change is negligible, hence it's reasonable to assume that mass is conserved in chemical reactions. For example, burning petrol releases about 44 megajoules for every kilogram. The mass equivalence of this energy will be given by mass is equal to energy over c squared. Putting in the values gives a mass change of 4.9 times 10 to the minus 10 kilograms. As a percentage, this comes out at just 4.9 times 10 to the minus 8%, clearly a negligible change. The mass change in nuclear decays is not negligible. Let's look at beta minus decay, where a neutron becomes a proton, ejecting an electron. To find the mass defect, if we consider the masses involved, here's the mass of the neutron that we start with, and the proton and electron that we end up with. There's also a neutrino, but this has 0 or negligible mass. So to find the mass defect, if we take the mass of the proton and electron that we end up with away from the mass of the neutron, we find the lost mass or mass defect. So the lost mass is given by the mass of the neutron minus that of the proton and the electron. And this comes out at 1.089 times 10 to the minus 30 kilograms. To find this as a percentage, divide by the mass of the neutron we start with and multiply by 100. This comes out at a much larger 0.06%, clearly not negligible. To find the energy released in this decay, we can use E equals mc squared, putting in the lost mass or mass defect in kilograms and the speed of light in a vacuum squared, gives an energy of 9.8 times 10 to the minus 14 joules.